Transistor characteristics. Common base configuration. The aim of our experiment is to draw the input and output characteristics of a common base configuration and hence to find the input resistance, output resistance and the current amplification factor. We are provided with an NBN BC107 transistor, and for the input side we are having a power supply, a rheostat, and to measure the voltage and the current, a voltmeter and ammeter. Similarly, for the output side, a power supply unit is here, a rheostat for varying the voltage, and a voltmeter and ammeter to measure the current and the voltage. And for the BC107 transistor, as you know, there are three leads are there: emitter, base and collector. We can easily identify the leads. The emitter side is provided with a small knob. So from that we are reading, the first one is emitter and then the base and then the collector. Here, for the purpose of giving connections, I have connected three wires to the emitter, base and collector. Here the blue is the emitter lead and the yellow one is the base and the green one is the collector. Now coming to the theory involved for the common base transistor characteristics. The input characteristics is defined as the curve drawn between the emitter current IE and the base emitter voltage VEB at a constant value of base voltage, base collector voltage VCB. Now from that graph we can find out the input resistance Ri, which is defined as the ratio of change in base emitter voltage to the emitter current at constant value of collector base voltage. Similarly, the output characteristics is the graph or curve plotted between the collector current IE and the collector base voltage VCB at constant value of emitter current IE. Now from the output characteristics we can find the output resistance RO using the condition or equation. It is the ratio of the collector base voltage to the collector current at constant emitter current, and that is calculated from the output characteristics. And the current amplification factor alpha, that is defined as the ratio of change in collector current, that is delta IC, to the change in emitter current, that is delta IE, that is delta IC by delta IE at constant value of collector base voltage. Now coming to the procedure part, we are provided with a BC107 transistor, and for this BC107 transistor, for base configuration, the base is grounded or the base is common and the base is grounded. Here we can see the base is grounded, and we have two sides, one the input side to find the input characteristics, and similarly the output side to draw the output characteristics. Now for when we consider the input side, so the input side is consists of the emitter and base. So we want to forward bias the emitter base junction, so the base is grounded. So the emitter of the NPN transistor is connected to the negative of a voltage supply. So we are connecting a 2 volt, a low voltage between the emitter and the base. So a voltage source is connected between the emitter and base. Now this voltage source is connected to the lower two terminals of the rheostat, the two terminals of the rheostat, and from the movable contact of the rheostat it is connected to the emitter. Then by moving the rheostat we can apply any value of voltage between emitter and base. Then to measure the current that is passing through the emitter, we are connecting a milliammeter, that is A1, ammeter A1 here. That ammeter A1 measures the current IE. Similarly, a voltmeter V1 is connected between the emitter and the base. A voltmeter is connected between the emitter and the base, and that voltmeter reads the emitter base voltage. The emitter base voltage is measured by the voltmeter V1, that is VEB. Similarly, in the other side, that is the output side, the collector base junction is there, that is to be reverse biased. For that the collector is to be connected to a little more high voltage of the order of 10 to 20 volt. So we are using a 20 volt supply, DC supply. that is connected to the two lower terminals of the rheostat. The movable terminal of the rheostat is connected to the collector. Then by moving the rheostat RH2, we can give different value of voltage, that is VCB, collector base voltage, to the collector side. To measure the collector current flowing, we are connecting a ammeter, milliammeter A2, and to measure the collector base voltage, the voltage between the collector and base, to measure that voltage we are connecting a voltmeter V2 that measures the VCB, the collector base voltage. Then when we are taking the readings, initially we are fixing to draw the input characteristics. The collector base voltage is fixed because by definition it is the curve drawn between current IE and VEB at constant value of VCB. So we are keeping VCB constant, say 2 volt. Then VEB, the base emitter voltage, is changing. When we are changing the base emitter voltage, the current IE changes. So for different values of base emitter voltage, say 0.1, 0.2, 0.4, 0.5, 0.6, etc., the current is determined. Now the experiment is repeated, changing the value of VCB to another value, say 4 volt. VCB is changed to a value of 4 volt, a constant voltage. Now when VCB is 4 volt, again we are finding the relation between IE and VEB, that is by changing the rheostat RH1, we change VEB. For each value of VEB, we find the value of IE. Again it is repeated for another value of VCB, that is 6 volt. For that also we are changing the value of base emitter voltage, and for each value of base emitter voltage the emitter current IE is determined. Then if you are plotting a graph, we are getting a graph like this. When the VCB, base emitter voltage, is 2 volt. Now we are plotting a graph between VEB along the x-axis and the value of IE along the y-axis. So we are getting a curve like this, the first one, the lower curve. When the graph is plotted for another value of VCB, that is when VCB is 4 volt, again the value of VEB and IE is plotted, that is the second curve. Then for another value of VCB, that is 6 volt, the graph is again plotted, that is the third one. Now from the graph we can find out the input resistance. From each curve we can find out, here it is find out from the second curve, the resistance is voltage by current. So that is delta VEB divided by delta IE. So here delta VEB is AB and delta IE is BC. So the reciprocal of the slope of the graph, that is AB divided by BC, gives the input resistance RI. Now we want to do the second part. We want to draw the output characteristics. So the output characteristics is already mentioned. It is the curve drawn between VCB and IC at a constant value of IE. Now for that, using the rheostat RH1, this IE is kept constant, say at 10 milliampere. IE is 10 milliampere. Now using the RH2, we are changing the collector base voltage. For each value of collector base voltage, we find out the collector current. Say VCB is equal to 1 volt, find the collector current. Say VCB is equal to 2 volt, find IC. VCB 3 volt, find IC, etc. So we are getting a relation between, or we are getting the readings between IC and VCB. Now it is repeated. We are changing the value of input current, that is IE is changed to a value of say 20 milliampere, keeping IE is constant. Again we are finding the different value of the collector current for different value of VCB. VCB is changing, and for each value of VCB we find the value of IC. Once again it can be repeated for another value of say input current IE is equal to 30 milliampere. Then also for different value of VCB we are finding the value of IC. So coming to the tableau column, we can see here. Now initially the input current IE is kept constant 10 milliampere. Then using the RH2, the collector base voltage VCB is changing 1, 2, 3, etc. voltage. For each value of VCB we are finding the value of the collector current IC. It is repeated. For another value of base current IE is 20 milliampere, the collector base voltage and the collector current is noted. Again for another value of IE is 30 milliampere, the collector base voltage is changed and the collector current is measured or noted. Then we are plotting a graph. We are getting a graph like this. Initially when the base emitter voltage is about say 1 milliampere, then VCB is plotted along the x-axis and the collector current IC that is plotted along the y-axis. Then you can see that for small change or values of VCB, the current slightly increases, and thereafter in the output characteristics the collector current, so this is IC, the collector current remains almost a constant. Now when it is repeated for another value of input current, that is say 2 milliampere or 20 milliampere, we are getting a different curve. For that the IC value is increased, but it remains a constant for higher values of VCB, but initially there is a small change or small growth in the value of current. Now again from this graph we can find out the output resistance RO, that is defined as delta VCB divided by delta IC, change in collector base voltage to change in collector current, that is equal to AB by CA in our graph. Now this AB gives the change in VCB. Now corresponds to AB, the change in collector current is C to A, that is CA. So AB divided by CA gives the value of the output resistance. Now we want to find out the current gain, the current amplification factor alpha, that is defined as delta IC divided by delta IE. Now in our graph delta IC is again CA, the change in collector current, that is CA. Then delta IE is the value of collector, the value of emitter current, sorry, the collector current at IE is equal to 4 milliampere, that is at C. Similarly, that is IE value at C, the emitter current, we want to find the delta IE. So delta IE is IE at C minus IE at A. Now in this particular graph, IE at C is 4 milliampere and IE at A is 2 milliampere. So delta IE is 4 minus 2, that is 2 milliampere. So that's a way of finding the change in emitter current, that is IE at C minus IE at A. Then we are getting the result, the input resistance, the output resistance, and the current amplification factor alpha, and the input and output characteristics are drawn. Now coming to the experimental setup of the common base configuration, you can see the diagram. This is the base is grounded. Now this is the input side and this should be the output side. Now here for the transistor, I already mentioned the yellow one is the base and blue one is the emitter and the green one is the collector. Now the emitter is grounded. Now we are taking a common terminal here on the breadboard or connection board. So that is grounded, and from that emitter to the output side, now this is the wire for the ground, and here this is the blue wire that is for the ground. For both the two sides it is grounded. Then from the emitter you can see, from the emitter we are connecting, from the emitter it is connected to the positive of a milliammeter. The emitter is connected to the positive of a milliammeter. From the negative of the milliammeter, now this should be the negative of the milliammeter, it is connected to the negative of the voltmeter, that is V1. From the voltmeter it is connected to the rheostat, the movable contact of the rheostat, that is a top connection. Then we have the potential divider arrangement. A voltage source is here. Now this should be the voltage source. So the two terminal of the voltage source is connected to the two lower terminals of the rheostat, the two lower terminals of the rheostat, and one of the lower terminal is grounded, it is grounded. So that is the input side, that is the input side. Now coming to the output side, now this is the output side. There also we are having a voltage source. Now this should be the voltage source. Now that voltage source is connected to the rheostat, the lower two terminals of the rheostat, and the upper terminal of the rheostat is connected to the voltmeter, and the voltmeter is connected to the milliammeter. Now here the milliammeter is connected here, and the negative of the milliammeter is connected to the collector. Now here the green is the collector. So this is the collector terminal. So the collector terminal is connected to the negative of the milliammeter. So that is the connection for the output side. Now in order to take the reading, initially we want to change the value VCB. VCB we can change with the help of that rheostat RH2. Now we can see the change. We can change the value of VCB. Now we can fix the VCB value at say 2 volt, 3 volt, 4, etc. So initially we are fixing the value of VCB at 2 volt. VCB is fixed at 2 volt. Now VCB is maintained a constant throughout for the first part, that is 2 volt. Now we are changing the input side rheostat is changing. Then if you are changing this value of VEB, that is RH1, we can see the voltage is changing. Now VEB value is changing. Now here VEB is equal to, now I am changing the value of VEB. Now when VEB is equal to 0.2 volt, the value of IE is 0, not started 0. When VEB is equal to 3 volt, again IE is equal to 0. When VEB is equal to 4, again we are getting 0. Then VEB is equal to 5, again we are getting 0. Then for VEB is equal to 6, again we are getting 0. And when we are getting, now VEB is equal to 7, now it starts reading. So before that we are taking one reading, say that VEB is equal to 0.68. Now for 0.68 I am getting a value of the IE value nearly say 6 milliampere. So the starting VEB is equal to 0.68, then IE is equal to 6 milliampere. Now again we are changing, VEB is changed to value of say 0.7. Now VEB is changed to value of 0.7. Then the collector current becomes a value of say 10 milliampere. Now this is 10 milliampere. Then VEB is changed to value of say 0.72. Now each division is 0.2 here. So 0.72. Then we have to maintain the output VCB 2 volt itself. Then for 0.72 I am getting a value of say 14 milliampere. Then for 0.74 the emitter current starts increasing, it is become a value of 20 milliampere. Then for 0.76 the milliampere is again increasing, so that is to 28, it is increased. Then say 0.8, now we want let us see what is happens for 0.8. Now the VEB value is 0.8. Now for 0.8, if VCB is changed, we have to fix it at 2 volt, then we are getting a emitter current of nearly say 48 here, so 48 milliampere. Then again it is changed, say again another value, say 0.84. Now it is 0.84 here, the VEB base emitter voltage. Then the collector current, emitter current is nearly 80 milliampere. So that values are recorded in our tableau column. Now we can repeat. Now we are changing the value of VCB. Now change the value of VCB to a value of say 4 volt. Now VCB is changed to value of 4 volt. So we have to maintain that VCB at 4 volt. Now again we are changing the input side. We are starting with 0.1 volt. Again we are IE is equal to 0. 0.2 IE is equal to 0. Say 0.4 IE is equal to 0. Say 0.5 IE is equal to again 0. For 0.6 now IE start reading. Now for 0.6 we are getting a value of say 4 milliampere. Then for 0.7 now IE is equal to 0.7. Sorry, VEB is equal to 0.7. So for VEB 0.7 I am getting a value of IE. Now that IE is 22. IE is 22 milliampere. Then we can take the other readings 0.72. IE is changing. IE is equal to 30. Now it is 30 milliampere. Then for 0.8. Now 0.8. So VEB is equal to 0.8 here. Then the emitter current IE is about 76. Then again the base emitter voltage is again changed, say 0.82. Now it is almost 100 or 96 milliampere. So up to which we change the value of input. Now once again we can repeat. We can change the value of the output voltage VCB to a value of say 6 volt. We are taking 6 volt here. 6 volt. Now again the input side is changed. So we are starting with say 0.1 volt. We are getting IE 0. So 0.30. For 0.4 volt it is also 0. For 0.5 6 volt it is now for 0.6 volt it starts. Now for 0.6 volt of VEB we are getting IE is equal to 10 milliampere. Then again we are increasing the value of VEB. Now when VEB is equal to 0.7 or in between we can take readings. When VEB is equal to 0.7 I am getting a current value of say 68 here, 68. So, when VEB is equal to 0.7 volt, the IE value is 68. Now, again we are changing the value of VEB to say 0.72. For 0.72, we are getting the milliammeter nearly 100 or 98 milliampere. So, with the help of RH1, we change the value of VEB and we find out the value of IE value at constant value of VCB. Now, we want to plot the output characteristics. For that, the input side is maintained a constant. That means the input current is maintained at 10 milliampere. The input current is maintained at 10 milliampere. Now, with the help of the rheostat RH1, the input current IE is maintained say 10 milliampere. Now, with the help of RH2, we are changing and finding the value of the collector current, collector current IC. Now, we can change the collector base voltage. Now, initially find what is the value. Now, bring it to 0.2 volt. Now, first two division 0.2 volt. Now, for 0.2 volt, now we have to maintain IE should be at 10 milliampere. IE should be at 10 milliampere. Okay. Now, we can see here. Now, IE is 10 milliampere. The voltage is say 0.2 or 0.4 volt here. Then IE is nearly 9 milliampere here. 9 milliampere. Now, you change. Now, you change the value to say 1 volt. 1 volt. 1 volt. Remain IE should be 10 milliampere again. Now, the value changes to a value of nearly 10 milliampere or 9 milliampere. Now, again change to a value of 2 volt. 2 volt. Now, this IE become 10 milliampere. Now, again change to 3 volt. Now, IE is remaining almost a constant. Now, IE is remaining almost a constant at 10 milliampere. Now, we change to 4 volt. Now, there is no change in the value of IE. So, IC, the IC remains a constant at 10 milliampere. So, for a particular value of input resistor, input current 10 milliampere, the output voltage is changed, VCB is changed. Then initially there is a slight increase in the value of IC, but IC remains a constant at 10 milliampere. Now, we can repeat it. For repeating, we are changing the input current. The input current is changed, say to a value of 20 milliampere. The input current is changed to a value of 20 milliampere. So, the input is kept constant. Now, change VCB value. So, take VCB value 0.2 volt. Now, for 0.2 volt, now it is reading a value of nearly 17 milliampere. So, that is IC. Now, change that output voltage to a value of 0.4 or 0.6, 0.4. 0.6. Now, it is nearly 18 milliampere. Again increase to 1 volt. 1 volt. Now, it is again nearly 19 only. 2 volt. 2 volt. Now, it is remaining a constant there. It is remaining a constant there at 19 milliampere. Now, again change 3 volt. Now, it is not changing. You can see that the IC becomes a constant here. It is become a constant here 19 milliampere for different values of VCB. So, 4 volt, 5 volt, 6 volt, etc. The IC remains a constant. So, initially it starts from 17, 18, etc. Then it becomes to a value of 19 and then thereafter it remains a constant. Now, once again we are plotting the curve for another value of IE. So, we are taking IE is equal to 30 milliampere. Now, initially IE, the input side is fixed. IE is equal to 30 milliampere. Now, we are changing the output side. Now, you can change the output side. VCB is equal to 0.2 volt. Now, VCB is equal to 0.2 volt. The ammeter reading is nearly 30 or 29 here, 29. Now, we change to 0.4. Now, 0.4. Again, it is 19. Then 1 volt. 1 volt. Now, it becomes almost 20 milliampere. 20 milliampere. That is IC value. Now, 2 volt. Now, it becomes a constant here. It is not changing, that is 20 milliampere. 3 volt, again no change. 4 volt, no change. 5 volt, 6 volt, we are changing value VCB. Now, IC is remaining a constant, 6 volt, 7 volt, etc. The IC value remains a constant. Now, you can plot the curve, the input and output characteristics. Now coming to a sample set of reading that we obtain in the common base configuration. For the input characteristics, we maintain the collector base voltage at 2 volt. Then we varied the emitter base voltage with the help of the rheostat RH1, and then the ammeter A1 that reads the emitter current. So initially for 0.1, 0.2, 0.3, 0.4, 0.5 and 0.6 volt, we obtain the emitter current as 0. So the emitter current starts when the base emitter voltage VEB becomes 0.68, we obtain a value of 5 milliampere. Then 4.7, 10 milliampere. Then 4.72, 14, 7.4, 18, 0.76, 20, 0.78, 28 and so on, 4.86, 80. Now with the value of this IE and the value of VEB, we plotted the first curve. Then again it is repeated. We took a value of VCB, collector base voltage 4 volt. There also we changed the value of VEB. Initially for up to 0.6 the emitter current is 0. Then when it is 0.7 the emitter current becomes 20, and thereafter it starts increasing. For about 0.82 the emitter current becomes 96. So the second curve is plotted with the help of these two values of VEB and IE input characteristics. Then in the for the third curve of the input characteristics, VCB is maintained at a voltage of 6 volt. We change the value of VEB, base emitter voltage is changed. Initially up to 0.4 volt the emitter current remains 0. Then it is 0.5 the emitter current starts flowing, that is 10 milliampere. 0.56 it is 20, and 0.7 volt it becomes 90 milliampere, and thereafter it gives a value higher than 100 milliampere. So that is about the input characteristics. So we plotted a graph here, that is for the common base input characteristics. So we obtained 3 curves. One is plotted at VCB 2 volt, the second one is plotted at VCB is equal to 4 volt, and the third one is plotted at VCB is equal to 6 volt. So 3 curves we obtained. So these are the 3 curves. So from all the 3 curves we can find the value of the input resistance Ri. So here we are plotting to find the input resistance, we are finding the slope, that is AB divided by AB is the delta VEB, and BC is the delta IE. So AB by BC we find out. For the first curve we are getting a value of say 2 ohm, and from the second curve we are getting a value of, from the second one we are finding a value of Ri is equal to 2.5, and here from the third curve we are finding the value of Ri, that is AB divided by corresponding BC, AB by BC, that is equal to 3 ohm. So we find the input resistance from the 3 curves. We obtain values 2, 2.5, 3 ohms. We find the mean value of input resistance, that is Ri. So that is 2.5 ohm. Then for the output characteristics, that is the graph or curve drawn between VCB, collector base voltage, and the collector current at a constant value of emitter current. So initially the emitter current is fixed as 10 milliampere with the help of the rheostat RH1. Then we obtain for the collector base voltage, say for 0.2 volt we obtain 10 milliampere, for 0.6 voltage we obtain 11, similarly for 1 volt 12, and thereafter it is observed that the collector current remains a constant 13 milliampere. So with the help of these two readings we can plot a curve or a graph between the VCB and IC. Then that is output characteristics. Then on the output characteristics the second curve is plotted, that is for another value of IE, that is 20 milliampere. Again VCB is changed, then IC also changed. Initially there is a small change. For 0.2 the collector current is 20, for 0.6 the collector current is 21, for 1 the collector current is 22 milliampere, and thereafter the collector current remains a constant 23. Similarly, when it is repeated for an IE value of 30 milliampere, the collector base voltage is changed, the collector current also changed, it remains a constant 34. So when we plot the graph, the common base output characteristics, we obtain the graph. It is plotted at 10 milliampere one, the other graph is plotted at 20 milliampere, and the third one is plotted at 30 milliampere. So for the first one, it is rising like this and remains a constant, and for the second one this is the curve plotted, and for the third observation tableau column this is the curve plotted. Now from this curve we can find the value of the output resistance RO. that is delta VCB divided by delta IC. Delta VCB divided by delta IC. Now for that we are using this part, the part say A, B, C, D I am using. So delta VCB, that is equal to A to B, because along the x-axis we are plotting the voltage VCB. So for AB, that means delta VCB, the change in collector current is CA, or A to C, that is CA. So AB divided by CA gives say 1.75 is the VCB voltage, and the milliampere current IC is 9 into 10 to the power minus 3. So we obtain a resistance of 194 ohm. Now the current amplification factor alpha is delta IC divided by delta IE, that is delta IC is again the CA, delta IC. Then delta IE is the value of IE. Now this is IE, the value of IE at C, that is say here it is 20 milliampere. Then value of IE at A, IE at A is 10 milliampere. So the difference is 20 minus 10, that is 10. Then alpha is equal to CA divided by 10, that is 9 into 10 to the power minus 3 divided by 10 milliampere. So that is equal to 0.9. So the amplification factor for the common base configuration is alpha is equal to 0.9. So we obtain the result, the input resistance, the output resistance, and the current amplification factor as 2.5, 194, and the amplification factor is 0.9.